Okay, welcome everybody to this colloquium of the Department of Human Movement Sciences. Today's colloquium will be presented by Koen Lemaire. And Koen was a student, a bachelor and a master and a PhD student in our department. He did his PhD under the supervision of Knoek van Soest, Richard Jaspers and Jeroen Smeets. And he worked on muscle tendon complex modeling in relation to the mechanical behavior and metabolic energy expenditure of muscles. After his PhD, Koen moved to Calgary to work with Art Quo, and he worked there on the mechanics of locomotion, and today he will update us on some of the work he has been doing there. I'm glad to say that Koen has returned to Amsterdam and joined our team again, specifically to work on the collaboration that we have with the University of Twente in their new curriculum in sports data science. Koen, the floor is yours.
Thank you, Jaap, for that kind introduction. So today I will be talking about the role of soft tissues in gait mechanics. And the background is that a popular idea of how we control our bodies is that the brain tends to minimize energy expenditure, metabolic energy expenditure. And well, this is a study by Selinger, but there are many studies showing that. And one of the key determinants of this metabolic energy expenditure, this is also well known, is positive mechanical muscle fiber work. However, when we consider walking, estimating this positive mechanical muscle fiber work is very difficult because over one gait cycle, there is no net mechanical work done on the body. So unlike in cycling, for instance, you cannot measure at the outside of the body what the mechanical work is. However, internally, there is both positive and negative mechanical work done. And the question is, how much? Well, there are grosso modo two approaches to this. One is using simple models and trying to estimate from that the mechanical work done, or using more complex models and inverse dynamics and trying to make a more explicit formulation of the joint work done. And in this talk, I will address both of these partly. So in part one, I will try to understand the head bobbing behavior of birds via an estimate of mechanical work in a simple model. And in part two, I will have a critical look at the mechanical works estimates done in inverse dynamics using more complex models. And all of the work I'm presenting today, as also mentioned by Jaap, is done in a collaboration with Art Quo and at the University of Calgary in Canada. Okay, part one. So here you see a video of a pigeon, all well known to us, of course, bobbing its head. And you notice that the pigeon keeps its head stationary intermittently and intermittently bobs it forward. And now the reason that the pigeon does this is because, unlike us, when I look at the screen and I move my head, my eyes can stay focused on the screen, but this is not the case for the pigeon. So when a bird wants to stabilize their retinal image, they actually need to keep their head stationary with respect to the world. And this is the cause for this behavior. Now, you can imagine if this is a footfall pattern of a bird, so left and right feet in time, and this is double support and single support, this head motion with respect to this footfall pattern we can represent as such. So you can have a hold phase and a thrust phase. And an observation in the literature is that this thrust phase is centered around double support. So when both feet are on the ground. And you may wonder, why is this? Because if this is the head velocity, in principle, you can choose any temporal relationship between the thrust phase and the gait pattern. So conceivably, you could shift this, right? And now the question is the timing of this head bob related to the mechanics of gait. Now, birds are complicated, obviously, so we set out to describe this by a simple model inspired by the literature. So in this landmark publication by Donlan and Kuo, it was shown that in this simple model, the collision amounts for a substantial amount of energy dissipation. And it is thus wise to try to minimize this collision. Now, a while after, Gomes and Ruina showed that in a model with distributed mass and some springy actuators, you can even achieve a completely collisionless gait. And the question is, do birds, inspired by this work by Gomes and Ruina, we can ask the question, do birds reduce the energetic cost by cleverly timing their head bob? Okay, so we set out to create this super simple model of a bird, which is essentially a rimless wheel, which you can view as an inverted pendulum with a fixed step length, which has a point mass head. Now, during the stance phase, this model is subject to pendular mechanics. So there is a ground reaction force, and there is gravity acting on the center of mass. Sorry, not the center of mass. There's gravity acting on the mass at the hip, and there's gravity acting on the point mass head. And in between the head and the hip, there is a massless neck with internal forces such that the head undergoes a horizontal motion with a velocity profile that we saw before. Now, during the step-to-step transition, there is an impulsive push-off and collision, and this has no effect on the head motion under the assumption that the neck actuator is limited. Okay, so with this model, we can make a simulation for a given head velocity profile. And then we can shift the forward thrust timings in this simulation. So we shift the forward thrust timing with respect to the footfall pattern. And this is an example of how such a simulation looks. So these are the legs and the head, and you see that we have a hold phase and a thrust phase. Sorry. Why is this? Okay, sorry. So in this simulation, we can look at the power in the neck actuator as a function of time. And for a given simulation, we can calculate the total amount of positive work done in the neck, and the total amount of negative work done in the neck, and add to that the power done during push-off and collision. And that gives us an estimate of the total positive and negative power per step. And that we see in this graph here. And now we did this for a certain forward thrust timing. And you can imagine we can do this for different forward thrust timings, like such or like such. And in fact, we can construct a graph of forward or work per step as a function of forward thrust timing, which looks like this. And as you can see, this graph has a distinct minimum of positive and negative work when the forward thrust timing is such that the thrust starts right before double support. Now, in the model, double support is of course instantaneous, but in reality, there is overlap between these footfall patterns. And from this, we concluded that for head bobbing birds, it makes sense to thrust their head forward right before the collision. And this is true if described by this super simple model. So at this moment, the bird should thrust its head forward. All right, that was part one. In part two, I will have a critical look at mechanical work estimates of inverse dynamics with this use of more complex models. And that's starting now. Okay, a key thing in inverse dynamics is that we use, we assume body is modeled, or we assume that the body consists of a collection of rigid bodies. And the question is, what happens if these bodies turns out not to be so rigid? And as you can see in this video, that might actually be of serious concern. So if you look at these slow motion images of a person running, it's clearly visible that that these segments or the body parts of this person are not quite rigid. Okay, so there has been work done on this before, notably by Zelic and Kuo, who quantified the difference between total mechanical energy and total joint work as soft tissue work or soft tissue dissipation. And this was continued by Fu et al., who found that this soft tissue work is increased in obese people, which suggests it might be due to some unmodeled wobbly mass motion or motion of tissue that is not rigid. And later, still even Honnert and Zelic found that this soft tissue work might be due to deformations in the foot, as we saw in the previous video. There's another part in literature which also deals with inverse dynamics, or another well-known problem in inverse dynamics, which is that your force plate recording may not agree with motion capture. And this is usually termed dynamic inconsistency and gives rise to residual forces in inverse dynamics. So you can imagine that with your ground reaction force, you essentially measure the acceleration of the center of mass. But with your kinematics, you could conceivably also compute the center of mass and then compute the acceleration of that same center of mass. And those two quantities might not necessarily agree. And that is perceived in literature as a problem. And there's also a solution to this problem, which is to fix those dynamic inconsistencies through optimization, basically tweaking the kinematics a little bit in such a way that they agree with the ground reaction forces. And I was wondering, well, we have these two sort of separate approaches to what seems to be the same problem. And is there a relation between these? Okay, so in this part, I'm going to do a quantitative test of this soft tissue work calculation, look at the relationship with residual force, and talk briefly about which anatomical structures might be responsible for this dissipation. So first, can we back calculate a known amount of soft tissue dissipation? But before we start all of this, I'm going to give everyone a very quick inverse dynamics analysis refresher, and this is of course super fun. So let's start. Inverse dynamics 101. Well, in inverse dynamics, we measure the movement of the body with motion capture. We measure the ground reaction force. Then we have some model of the human body, which is usually some sort of rigid body stick figure. Then we use the laws of Newton. And then we use the laws of Newton to calculate all kinds of variables like joint moments, joint reaction forces, joint powers, and what have you. So let's focus a little bit on these laws of Newton, which are at the core of all this business. So a super short summary of mechanics is that for each collection of masses, we have linear momentum balance, which says that the sum of all forces acting on this collection equals the mass times the acceleration of the center of mass. And we have angular momentum balance, which says that the sum of all moments with respect to some points equals the rate of change of angular momentum with respect to that point. And when you think about momentum, you can think about this as mass movement. So a train, a freight train that's going fast has a lot of momentum. Now, in our for a walking human, this sum of forces equals the ground reaction force and gravity, and the mass times acceleration of the center of mass comes from our model and the distribution of the masses in this model and the velocity of each of these segments. So that is our model plus our motion capture recording. And the difference between those two quantities you might call dynamic inconsistency, residual forces. This leads to an overdetermined system, etc. But what does this mean for the mechanical energy involved in this system? Okay, to think about this, we need to first refresh our energetics knowledge. So the mechanical energy balance for a single rigid body is relatively straightforward. The work done by all external forces and torques equals the change in the kinetic and potential energy of this body. This is relatively straightforward. Now, for a multi-segment body or non-rigid body, because these segments can move with respect to each other, there is not only work done by external forces, but there can also be work done by internal forces. And again, this total collection of work again equals the change in kinetic and potential energy of a non-rigid body. And the essential difference then is that in a multi-segment body, internal forces and moments can do work, joint work. And this is the reason, of course, why we as humans can move and jump and do stuff, because our segments move with respect to each other and our muscles then exert forces on those segments. Okay. So we found that the mechanical energy balance for the human is that the sum of all work done by external forces plus the sum of all work done by internal forces equals the change in kinetic and potential energy. Now, when walking, the work done by external forces is the ground reaction force and gravity, obviously, because those are the external forces acting on our human. But over one cycle, they do net zero work. And the internal work done, you might call, is what we usually refer to as joint work. And then the kinetic and potential energy change we can derive from our segment model as well. So if all is well, in the ideal world, our joint work should equal the change in kinetic and potential energy, because if we look at this equation and if our external work is zero, then these two must be equal. However, this is generally not the case when you do inverse dynamics. And this is because of these inconsistencies. Joint work does not equal total mechanical energy change. Okay, so what is a solution to this? Well, we can estimate this total energy change by taking the kinetic and potential energy of the center of mass, which is based on our force plate recording. So in literature, this is also referred to as center of mass work. And we can add to that the kinetic energy with respect to the center of mass. So you can take the motion of all your segments with respect to your center of mass, and then that motion represents some kinetic energy with respect to a reference frame that's fixed to the center of mass. And this is based on our kinematics recording and our model. And this is also usually referred to as peripheral energy. And then take this measure, and if you then subtract from that your traditional joint work, which is based on rigid bodies, you get what is soft tissue work. So this is the essential idea of that method. And then the key is that the center of mass plus peripheral work is assuming, less rigidity than this joint work. So the center of mass plus peripheral work is related to the whole body because your force plates don't care about your rigidity assumption, right? They are agnostic to that. Whereas your rigid body model does have this rigidity assumption. All right. 3 deep breaths and a sip of water for me. To let that sink in. And now we get to the meat of this first part here. Okay, so to explore this, I did an experiment where I deliberately added soft tissue work to the body by means of these air pump under the feet. And I tried to back calculate the energy dissipated in these air pumps using the aforementioned methods. And so we did standard inverse dynamics measurements, and then we did an independent experiment with the air pump separately to quantify the amount of compression in each step. And all mechanical energy terms I will be talking about today will be expressed in a treadmill-bound reference frame. Okay, let's watch a video of how this experiment looks. Switch on your sound if you haven't already. All right, so as you can see in this video, there is massive dissipation going on. There's sounds, there's noise, airflow, compression, contraction, whatever you want. So it's clear that these air pumps involve massive dissipation, which is soft tissue work, which would not maybe be captured by our traditional rigid body assumptions. And this is also what we see. I will talk you through these graphs. At the top here, you see the ground reaction force in body weights for the normal condition and the air pump condition. And then the red lines are the left leg and the right, or the green lines are the right leg. And different lines are different speeds. Okay, then here you see the center of mass power. So what you can think of what this is essentially the rate of change of kinetic and potential energy of the center of mass. So this is the bulk of the energy fluctuations in your body as a function of time. All of this is as a function of time expressed as a percentage of gait cycle with respect to left heel strike. Okay, and then here at the bottom, you see center of mass plus peripheral power, which is like the rate of change of the total mechanical energy of the system, or an estimate thereof. And then when you compare this total mechanical energy with this joint power, you see that there are, in the air pump case, there are large differences during early stance, which is when you start to decompress the air pump. And that you can also see that this leads to large soft tissue power during early stance. And then if you look at, if you integrate this power over time, you can look at the work done per step. And then we see that in the air pump case, there is much more soft tissue work done, which is the circles here. And negative soft tissue work done, which makes sense because there is dissipation in the air pump, and positive joint work done, whereas the total change in mechanical energy is close to zero, which it should be because it's, of course, periodic motion. Okay. Now, I promised we would test this against an independent measure of air pump dissipation, which looked something like this. So I just compressed the air pump and then placed some markers on my foot to estimate the point of application of the force acting on the air pump. And then assuming the air pump has zero mass, we can multiply this point of application with the velocity. Sorry, we can multiply the velocity of this point of application with the force acting there, and that gives us a measure of power. And if we then integrate that power, we get a certain amount of positive and negative work done by the air pump. And that agrees reasonably well with the estimate of soft tissue work during our walking trials. All right, so that was part one of part two. That this calculation agrees relatively well with an independent quantitative measure of soft tissue. Now, how about this relationship with residual force? So we were comparing these apples and oranges, and then tried to, which was the reason for this residual force, for this soft tissue work. So our expectation is that residual force will increase when soft tissue work increases. So to address this, I looked at data of normal walking across a larger range of speed. And the expectation was that higher speeds will result, well, first of all, in larger ground reaction forces, larger energy fluctuations, more soft tissue work, and larger residual forces. And this is also what we found. So this graph has the same layout as the graph we saw before. So the top panels are ground reaction force. The center panels are center of mass work. So the rate of change, center of mass power. So the rate of change of kinetic energy of the center of mass. And the bottom panels are again the rate of change of total mechanical energy of the body. And then we see indeed that we have larger ground reaction forces for faster speeds, which are here represented by more opaque lines. We also have larger energy fluctuations, as seen in the bottom graph, for higher speeds. Well, do we also have more soft tissue work? Oh, sorry. Yes, we do. So we have, as you can see here, there's larger soft tissue power, again, during the early phases of stance. And when we integrate this power, this also leads to larger soft tissue work, as seen here. And finally, do we also have larger residual forces? Here we see a graph of, again, ground reaction force on the top panels. And now the middle panel is the magnitude of the residual force, which is basically the discrepancy between mass times acceleration of the center of mass as calculated from our inverse dynamics, and the sum of forces as calculated from the ground reaction force and gravity. And we indeed see that for larger velocities, larger walking speeds, we have larger magnitudes of this residual force and also larger magnitudes of the residual moment, which is shown in the in the bottom panels. So this seems to check out. So we can perhaps from this conclude that residual forces are related to soft tissue work, but actually we don't really see that in the air pump condition, right? Because when the soft tissue power is large in the air pump condition, we barely see spikes in the residual force, which might which is a little bit surprising perhaps. And the reason why that is that, well, if you imagine the air pump to be a massless damper, then it will not show in the force equation. It will not contribute to the acceleration of the center of mass because it has no mass, but it will contribute to energy dissipation because it's a damper. And that's the reason why this residual force is only affected by wobbling mass, but not by dissipation in a massless damper type of structure. Okay, so as for the second question, is there a relationship with residual force and moment? For wobbling mass, yes, but not for massless damper. Then the final part is, where is the energy dissipated? Well, there is some evidence that this soft tissue work is mostly related to wobbling masses. And the biggest evidence we have for that is this residual force, because you can imagine that residual force basically, well, it can have several causes, but one of them could be unmodeled mass motion. And one study that suggested we should look in this direction is that soft tissue work is indeed increased in obese people, which was investigated by Fu et al., although they did not make a comparison to residual force. The second point is that soft tissue work is increased with speed, and you can imagine that if you walk faster and you have higher ground reaction forces, you have more wobbling mass. And as we also saw, is that the speed-related soft tissue work increase is related to larger residual forces shown in this study. So altogether, I think there is good evidence for wobbling mass as a source, or I should say cause, of energy dissipation. But also, as you can see in this video, there is pretty substantial deformation of the foot. And that has been investigated by Honert and Zelig, who claim that the foot and shoe is responsible for the majority of soft tissue work in early stance. And actually, this is consistent with the measurements that we did in the air pump walking, because the air pump you can maybe see as I mentioned before, as a sort of massless damper that dissipates energy. And in our case, for normal walking, the energy dissipation in the air pump you can quantify with a thing called distal foot power, or work in this case, which I took here from Honert and Zelig. And for normal walking, this is partly in line with that. Okay. Okay, now, so this was all, seemed to all check out, but there are some issues with this method, which I do want to briefly mention. And the main thing is that this, in general, joint torque or power over work is not uniquely defined in standard whole body inverse dynamics if there is in the presence of residual forces. And this is because your joint torques will depend on which segment the residual force or moment is assigned. So you can imagine that if you have a discrepancy between your force plate and your kinematic model, this gives rise to some residual force, but you have to decide when you do your analysis of your kinetic analysis, so calculating joint torques, you have to decide on which segment to apply this residual force. And it's not self-evident from the data what the best choice is in that. So this is essentially an arbitrary choice. And this means that, but that choice will affect your joint torque. So this means that joint torque is in some sense not well defined, and thereby joint work is also not well defined. And so one example that you might know in this context is that in standard inverse dynamics, you will compute your force and moment balance from the feet and then progress to the head with the residual appearing at the head. But you could conceivably also start from the head and then your residual appears at the feet, and that will give a different result. And that's of course unpleasant because, yeah, if you quantify something and you define something, you would like that definition to be unique. And this, the unfortunate thing here is that what is best will depend on details of the system, but we actually don't know these details. That's exactly the reason why we are trying to estimate these variables. So this is a nuancing remark with the previous story. So I would say that soft tissue work represents foot deformation and wobbling mass, probably. And I would like to acknowledge at this point Eric Honnert, with whom I collaborated on this project as well. So our quantitative test of soft tissue work calculation agreed with our independent measure of foot air pump. Was there a relationship with residual force? Yes, but only for the wobbly mass case. And where is this energy then dissipated? I would say in the foot and in wobbling masses, and it is not totally clear how the distribution is between these two sources. Okay, so I see I have even time left. In this talk, I talked about, in part one, about head bob timing in birds, which might be such that the energy dissipation in collision is avoided. So birds might time their head bob with respect to their footfalls in such a way. And in part two, I argued that inverse dynamics, traditional inverse dynamics, likely underestimates the mechanical work done. I added here bimuscle tendon complexes because this was a discussion about joint work. So this is essentially network by muscle tendon complexes, probably due to soft tissue dissipation. And I think to get a better handle of that in the future, I would like to combine experimentation and forward dynamic modeling to further solidify these findings. And with that, I would like to acknowledge all of the people on this slides who were my colleagues in Calgary, friends and colleagues in Calgary. And I would like to thank you for your attention, and I'm happy to take any questions.
Okay, thank you very much, Koen. Before we go into other questions, I had a question, but you actually answered it on your conclusion slide, because you said that the pigeon does initiate the head bob just before foot strike, or is it? I don't know. Is it called a foot in the birds? Yes, I guess it is.
Well, perhaps. I don't know, actually. Yeah.
Anyway, but you didn't mention whether that would be. I mean, sorry, you mentioned that would be optimal, but you did not mention that they actually did it. But I think in your conclusion slide that you said that those two match.
Yes, they do that.
All right. Any other questions? If you have a question, please feel free to use the reaction button. And you will immediately turn up at the top of the screen and you can ask your question. All right. Well, while we're waiting, Koen, you showed that this soft tissue power, I think in slide 53, it was not very symmetrical if we look at the left and right heel strike, whereas the residual forces seemed to me symmetrical. That must have been an earlier slide, sorry.
Let's see if we can find that.
Yeah, it's somewhere here, one of these time series, I think a bit later. Soft tissue power, yeah.
Here,
yeah.
I guess, huh?
So we see a negative peak around the first heel strike, but not around the second heel strike.
That's a good observation. We also noticed that, and I think, so this was actually based on a measurement on myself, and it appears that my gait pattern, so we tried to delve into this and try to figure this out, but it seems that my gait pattern is just somewhat asymmetrical.
Okay, well, it seems to normalize when you walk on air pumps, so maybe you should do that.
That's a good point, yeah.
But the residual forces seemed quite symmetrical. Were those from the same data?
Yes, yes, yes. All from the same data. Yeah.
Okay.
Do we have that?
I think it's one later, probably.
Oh, it's later. Yeah, you're right.
There you go.
Yeah, good point. Although I would say that, yeah, no, they are symmetrical. Yeah.
I see Itzhak has a question. Maybe we should.
Yes, thanks, Koen, for your nice talk. I'm a bit confused about the peripheral kinetic energy concept. Maybe I misunderstood a bit. Suppose you have unequal velocities of segments, then it is always the case that your kinetic energy of your body center of mass is smaller than the summed kinetic energy of your body segments because of the square in the half mv squared.
Yes, for sure. Yeah.
But that has nothing to do with soft tissues, and it seems that you equate them.
Okay, no. So imagine that you have two masses. Okay, your system consists of two masses and they have a different velocity each. Then you can represent the kinetic energy of this system by either adding the energy of the two masses together.
Yeah.
Or you can consider the velocity of the center of mass and calculate the kinetic energy associated with that and add to that the relative velocities of the masses with respect to the center of mass. And that's also your total kinetic energy.
Yeah, sure. I understand that. Okay.
Yeah.
But the difference when you don't take the peripheral kinetic energy, then that's the difference is not the same as soft tissue work, right?
Sure, exactly. That is true. Well, okay. Maybe there's a mix up here. So the soft tissue power here is the difference between the center of mass plus peripheral energy. So that's an estimate, or power. So that's an estimate of this rate of change of total energy.
Okay. Yeah.
And the sum of joint power, which comes from your traditional inverse dynamics.
Okay. Yeah.
No.
Now it's
Good
clear.
point.
Thank you.
Yeah.
Okay, Pasha has a question.
Hi, Koen.
Hi.
Love seeing the pigeon talk again. I had a question about your inverse dynamics analysis. You mentioned that, well, you treat everything like rigid segments as we always do. What about the joints? Are the joints like fixed hinges, or are you doing some type of instantaneous center of rotation thing?
Well, in this study particularly, I did what they call 6 degree of freedom joints. So there was translation allowed in these joints.
Pasha, can you mute? Because
Sorry.
there's a lot of...
So there was translation allowed in these joints. Does that answer your question?
Yes, it does. Yeah. So
Okay.
it's not a simple hinge, so it's not like some of the residual forces coming from that simplification.
No, exactly.
Okay, thanks.
Any other questions or comments?
Yeah, I have a question for Koen.
Please.
So I was wondering, so I assume that the center of mass power is calculated by multiplying ground reaction force with the velocity of the center of mass. Is that right?
Correct.
How valid is that? Because if I remember correctly, power is calculated by multiplying the force with the velocity of the point of application, but the ground reaction force does not apply at the center of mass.
Sure. So this is what this actually means. If you work this out, it turns out that this means, or this is equal to the rate of change of kinetic and potential energy of the center of mass. And I know that you are quick with these things, Roland. If you grab a pen, okay, you will write down F gravity plus F ground equals mass times acceleration of the center of mass, okay? Now multiply left and right with the velocity of the center of mass. Right.
Mhm.
Now move the term gravitational force times velocity of the center of mass to the right hand side, and then you can see that this is actually equal to the rate of change of kinetic energy, right? Which is half mv squared, and then if you differentiate that, you get mv acceleration. Yeah.
Right. Thank you.
Agreed?
Yeah.
Yeah. Yeah.
All right. Nice demo that not everyone needs a piece of paper and a pen to actually do this. Good. I see Nick has a question.
Yes. Hi, Koen. I was wondering, so you showed that the soft tissue during faster walking is basically contributes more to or has a larger contribution. I was wondering, when you're walking faster, do you have also more skin artifacts and that sort of stuff that could introduce this larger that it looks like soft tissue contribution, but it's instead just more marked motion and skin artifacts? Or am I seeing this wrong?
This is an excellent point, Nick. I don't think you're seeing this wrong. So I think in general, so we did observe an increase with an increase of soft tissue work with speed, right? This is just an empirical observation, but it's not, which was also in line with expectation, but it's not guaranteed that there is a causal relationship here. Exactly because of the things that you say. So it might be that this increase is due to all kinds of other things that you misrepresent in your measurement.
Yeah.
Right, because in some sense we are lumping here errors of, let's say, misestimating inertial parameters, misplacing markers, what have you more. All of these things are, of course, present in this residual force and also in this soft tissue work. Yeah. So I agree with you that this is not a definitive proof, but more a correlation in that sense.
Right, thanks.
Good point. Yeah.
All right. Any other questions or comments? If not, I would like to thank Koen for this presentation and everyone for their questions and attention. So hope to see you at the next colloquium in about a month's time.
Okay. Thanks, guys. Ciao.